Hello, and welcome to this new session on the abstraction of cyber attacks. Today, we will examine the structured progression of cyber threats, tracing their evolution from initial reconnaissance to the full compromise of systems. A thorough understanding of this process is essential for security professionals, information technology practitioners, developers, and organizational leaders who are responsible for safeguarding digital assets and anticipating the ever-changing tactics of adversaries in the cyber domain. Cyber attacks are often misconstrued as random or opportunistic events. In reality, they are deliberate, highly organized operations that require careful planning and technical expertise. Threat actors, sometimes referred to as attackers, select their targets with precision, conduct extensive research to uncover exploitable weaknesses, develop or acquire specialized attack tools, and execute their plans in a methodical manner. This sequence of activities, commonly known as the attack cycle, is central to understanding how cyber threats emerge and succeed. The process typically begins with the identification of a target. Threat actors utilize a wide array of resources to search for vulnerabilities. Technology vendors such as Microsoft or Red Hat routinely publish security advisories or vulnerability reports, which detail issues discovered in their products. Security researchers, including ethical hackers or penetration testers, play a vital role by identifying vulnerabilities and reporting them to vendors in a responsible manner. To encourage this behavior, many organizations have established bug bounty programs, which are structured incentive schemes that reward researchers with monetary payments. These rewards can range from several $1,000s to tens of thousands of dollars, depending on the severity or impact of the vulnerability. This collaborative approach accelerates the discovery and remediation of critical flaws, strengthening the overall security ecosystem. After a vendor releases a security patch to address a vulnerability, the dynamics of the threat landscape shift. Threat actors often engage in reverse engineering of these patches. By analyzing the code changes introduced by the patch, they can deduce the nature of the original vulnerability and develop new exploits targeting systems that have not yet applied the update. The period between the release of a patch and its widespread adoption, often referred to as the patch gap, presents a significant opportunity for attackers. Exploits developed in this manner are sometimes published openly on platforms such as GitHub or exchanged in underground forums or dark web marketplaces, fueling a global network of cybercrime. A considerable number of these exploits are aimed at outdated or unsupported systems. In many industrial settings, legacy technologies such as Windows XP continue to operate critical infrastructure. These systems often lack modern security controls and are infrequently updated, making them attractive targets for attackers. The WannaCry ransomware outbreak serves as a prominent example of the consequences that arise when known vulnerabilities in obsolete systems remain unpatched. This incident led to widespread disruptions across healthcare, logistics, and government sectors, highlighting the importance of timely patch management. Identifying vulnerable targets requires more than simply possessing an exploit. Threat actors employ specialized tools to conduct large-scale reconnaissance across the internet. One notable tool is Shodan.io, a search engine that indexes internet-connected devices rather than traditional web pages. Shodan enables both attackers or defenders to scan for exposed servers, databases, industrial control systems, or various network devices that are accessible online. For example, a threat actor seeking to compromise an organization running Oracle Enterprise Resource Planning software could use Shodan to locate publicly exposed Oracle ERP systems with known unpatched vulnerabilities. On the other hand, proactive organizations use Shodan to audit their own digital footprint, identifying and correcting misconfigurations before they can be exploited. Shodan's continuous scanning provides valuable real-time insights into the types of devices, open ports, or system configurations present on the internet, empowering both sides of the cybersecurity equation. A solid grasp of how cyber attacks unfold is foundational for building effective defense strategies. Security professionals often rely on structured models to analyze and anticipate the progression of attacks. Among these models, the cyber kill chain is especially influential. The kill chain breaks down a cyber attack into a series of distinct sequential phases, each representing a critical step from initial reconnaissance to the attacker's ultimate objective. The cyber kill chain breaks down a cyber attack into a series of distinct sequential phases, each representing a critical step from initial reconnaissance to the attacker's ultimate objective. The first phase, reconnaissance, involves gathering information about the target. Attackers use both passive or active techniques. Passive reconnaissance includes collecting data from public sources, such as IP address registries, corporate websites, or social media platforms like LinkedIn. This can reveal valuable details, including the technologies an organization uses, its personnel structure, or recent changes in its security posture. For instance, if an employee announces on LinkedIn that they have completed a certification in Fortinet technologies, it signals to an attacker that the organization likely employs FortiGate firewalls. This information allows the attacker to tailor their approach, seeking out known vulnerabilities in those products. Active reconnaissance, in contrast, involves direct interaction with the target's network infrastructure, such as scanning for open ports, services, or system banners that disclose software versions and configurations. After reconnaissance, attackers proceed to the weaponization phase. During this stage, they create the tools or payloads needed to exploit their target. This may involve developing custom malware, embedding malicious macros within seemingly harmless documents, or crafting exploit-laden images in websites. A common scenario is the embedding of ransomware or remote access trojans within an email attachment or a file that appears legitimate. These payloads are engineered to bypass security controls and deceive unsuspecting users. The next stage, delivery, focuses on transmitting the weaponized payload to the target environment. Attackers use various channels for delivery, such as spear phishing emails, malicious websites, infected USB drives, or compromised supply chains. Each method presents unique advantages or challenges. For example, phishing is effective because it exploits human trust, while supply chain attacks can compromise software before it reaches the end user. Once the payload reaches its destination, exploitation occurs. This is the pivotal moment when the attacker's code is executed on the target system, leveraging a vulnerability or a social engineering tactic. Exploitation may involve techniques such as buffer overflows, privilege escalation, or exploiting weak authentication protocols. The success of this phase often depends on the attacker's ability to circumvent existing security controls, underscoring the importance of layered defenses and comprehensive user education. Following successful exploitation, the attacker moves to the installation phase. The objective here is to establish persistent access within the compromised environment. This typically begins with the deployment of a dropper, a small program that downloads and installs additional malicious components, such as ransomware, spyware, or remote access tools. Attackers may also take measures to conceal their presence using rootkits or altering system logs to evade detection. With persistence established, the attacker seeks to achieve command and control. This involves connecting the compromised system to an external server under the attacker's control. Through this communication channel, the attacker can issue instructions, exfiltrate sensitive data, or coordinate lateral movement within the network. Command and control channels are often designed to blend in with normal network traffic, using encrypted communications or commonly used protocols to avoid detection. The final phase of the kill chain, actions on objectives, is where the attacker executes their primary goal. This may involve stealing proprietary information, encrypting data for ransom, sabotaging operations, or using the compromised system as a platform for further attacks. Data exfiltration is particularly common, with attackers targeting financial records, intellectual property, customer databases, or trade secrets. The consequences of such breaches extend beyond immediate financial loss, affecting reputation, regulatory compliance, and the long-term viability of the organization. It's important to recognize that not all attacks follow the kill chain in a strictly linear fashion. Some steps may overlap or repeat as attackers adapt to defensive measures. To address the evolving tactics of threat actors, security practitioners increasingly rely on frameworks that provide detailed insight into attacker behavior. The MITRE ATT attack framework is a leading example. Unlike the kill chain's high-level approach, MITRE ATT attack breaks down the tactics, techniques, or procedures, often abbreviated as TTPs, used by attackers at each stage of an intrusion. This framework offers a comprehensive matrix of attacker actions, from initial access to lateral movement or data exfiltration, mapped to real-world observations of cyber threats. For example, during the privilege escalation phase, attackers may use techniques such as credential dumping, where they extract authentication credentials from memory or system files. With these credentials, they can impersonate legitimate users and move laterally across the network. Defending against such tactics requires a combination of technical controls or operational vigilance. Organizations can implement strong authentication policies, deploy endpoint detection and response solutions, and continuously monitor for unusual account activity. Another technique is lateral movement through methods such as pass the hash, in which attackers use stolen hashed credentials to access other systems without knowing the underlying passwords. Real-world breaches experienced by large retailers or government agencies have frequently involved such techniques. MITRE ATTK not only catalogs these methods, but also provides actionable defensive recommendations, enabling organizations to develop targeted controls, train staff, and conduct realistic attack simulations. Abstracting cyber attacks into structured models like the kill chain or MITRE attack is invaluable for organizations aiming to build resilient defenses. By understanding the sequence of steps and the specific tactics used by attackers, security teams can proactively design layered controls, conduct threat hunting, and prioritize remediation efforts. This approach is especially relevant in professional environments where regulatory requirements, customer trust, or critical operations are at stake. Nevertheless, the challenges remain significant. Attackers continually innovate, leveraging automation, artificial intelligence, or newly discovered vulnerabilities to bypass even the most advanced defenses. The emergence of ransomware as a service, supply chain attacks, or cloud-based threats demonstrates how the attack landscape is expanding in both scale and complexity. Defenders must keep pace by continuously updating security controls, managing patches promptly, and fostering a culture of security awareness throughout the organization. To address these challenges, organizations should adopt a proactive and adaptive security posture. This includes sharing threat intelligence with industry peers, deploying zero-trust architectures that assume no implicit trust within the network, and utilizing machine learning to detect patterns of malicious activity. Regular penetration testing, comprehensive vulnerability management, or ongoing user education are essential elements of a robust defense strategy. In highly regulated sectors such as finance or healthcare, adherence to best practices is not only a security necessity, but also a legal and ethical obligation. In conclusion, understanding the abstraction of cyber attacks, including how they are conceived, executed, or defended against, is fundamental to modern cybersecurity. Structured models such as the cyber kill chain or the MITRE ATTAK framework provide powerful perspectives for analyzing and countering threats. By internalizing these concepts, professionals are better prepared to anticipate attacks, implement effective controls, and respond decisively to incidents. The stakes are high, but with knowledge, vigilance, and collaboration, organizations can strengthen their defenses and better protect their